Okay, so if we look at this calculation, if I compare this line that I've just underlined in red to this line that I've just underlined in red, then I can draw a conclusion. And the conclusion that I draw is that K, phi of naught, naught, is equal to lambda K, phi of naught, naught. Now, let's think about what K and lambda K are. So K is a state which has momenta K naught and spatial K, so a total of 4 numbers. Lambda K are those 4 momenta in some other inertial frame. And by picking a suitable Lorentz transformation, I can turn one K mu into any other K mu. And I learned that this number is exactly the same if I evaluate this function at any value of K mu. So what I've learned is this quantity over here is a number, okay? And what I mean by this is it's not a function of K mu. So maybe I should say it's a constant number, not a function of K mu, okay? And it typically gets a name. It's typically called Z to the 1/2. And the reason why we call it Z to the 1/2, oh, by the way, I should make an important comment. There's something that I should have mentioned, but I didn't mention it. So let me mention it right now. What I'm doing now, everything below the blue line, now for the first time, I specialize to a one particle state, okay? And, well, I haven't said anything yet that's special to the one particle state, but I'm about to, okay? So here we've got Z to the 1/2. Why did we call it Z to the 1/2? It's so that I can call this quantity Z. Z is K phi of naught, naught mod squared. Now, what is this? So let me first of all tell you what its name is, and then we'll talk about its physical interpretation. So this is called the wave function renormalization. And in a few recordings' time, you'll be able to understand why this is its name. But for now, just accept it as a name. It's called the wave function renormalization. And now I'm going to use the fact that we've specialized to a one particle state. So what is the state naught? Okay, the state naught is the state with no particles. So it's the no particle state. Now, what is the state phi of naught on naught? Now, you might tell me that what phi does is it creates a particle. And that's true in the free theory. If you're in the interacting theory, though, this state phi of naught on naught will not be a one particle state. It will have a one particle piece, but then there is also all sorts of multi-particle garbage. Okay, so multi-particle piece. So there'll be a two-particle piece, three-particle piece, and everything else. And what I've done in this quantity Z is I've taken this multi-particle state, one particle plus particle state, and I've projected out the one particle piece by calculating the overlap with state K. Now, you might say, oh, you're working out the probability that you've got a single particle with a certain momentum K. Well, that's not true because, as we just argued, this quantity is independent of momentum. So the physical interpretation of this quantity is that this is the probability that phi of naught creates a single particle state. Okay? So phi of naught will create a complicated multi-particle state, Z tells us the probability with which we create a single particle piece. And because it's a probability, we certainly should expect that it lies between the values 0 and 1. And if we can find this, if we can check this, this would be evidence for our interpretation. And what we are going to be able to show later on, using nothing more than Poincare invariance, we are going to show that Z does indeed lie between 0 and 1. So we're going to show it on very, very general grounds. Okay? So let's just summarize what we've achieved, because we did achieve some important things here. So let me just write here, summary. And these are the takeaway messages that I want you to keep with you. So here's the first one. I'm going to start putting an N here. And the reason for that is I want to start distinguishing how many particles we've got. Okay, so N is going to stand for the number of particles. And we calculated this matrix element, and this was e to the I kn dot x, and we had kn phi of 0, 0. So this we proved. And just to stress my notation, Kn is an n particle state, and also it's an eigenstate of H, the Hamiltonian, and the momentum operators. Okay, then we said, so we specialized, specialized to a single particle, so n is equal to 1. And in this case, we said K1 phi of x naught is equal to Z to the 1/2 e to the I K1 dot x. And Z, of course, is the mod squared of this quantity, phi of x naught. That's squared. And this we've already shown is independent of K1 mu, that four momentum. And we said that it's got a specific name. This is called the wave function renormalization. And what did we say? This tells us the probability with which phi of naught creates a single particle state. And because of that, we said we expect Z to lie between 0 and 1. So I really want you to be very familiar with everything that we've put here in the summary, with what the wave function of normalization Z is, and because of that interpretation, why we expect it to lie between 0 and 1. Good. We'll continue in a moment.